He has done obviously fantastic work in computational statistics and their applications, I may say. For me, it was amazing that he developed this lovely methodology for what we call, at least some of us, unadjusted Langevin algorithm, but Arnak likes, I think, the expression Langevin Monte Carlo, which is also very nice. Fantastic work, Arnak. So it was a great pleasure to have you here. And let me give Arnak's title of the talk, which is Langevin Monte Carlo, and now focused against on a randomized midpoint method. Okay, so the floor is yours.
Thank you very much, Sotirios, for this very kind introduction, and thanks to Denise also for inviting me here. It's a great pleasure to be here and to present this work. So I have to stress right away that the work that I will present now will be largely revisiting already known stuff. At the very end, I will talk a little bit about some very new results which are not yet on the net. So it will be on the net in the coming weeks, I think. And I would like also to stress another point. So the title of the workshop is Accelerating Generative Models and Non-Convex Optimization. So generative and optimization are two keywords that you will find in my talk, but I am not necessarily accelerating generative models, and I am not necessarily doing generative modeling in this talk. However, I will try to stress that some elements that I present in this work can serve in the future for doing some acceleration. Another point that I would like to just quickly mention in order to explain what is kind of philosophical difference between what I am presenting here and some other talks that you have seen before is that I'm not necessarily here interested in doing generative modeling in the sense of ChatGPT or DALL-E or generating images or texts, where basically you have no measure of evaluation for knowing whether your generated examples are good or not. I am rather interested in the situations where you have to be very careful with the way you are using MCMC. And you want to be sure that the MCMC algorithm that we have used has some guarantees. So basically, probably dimension is not very large. Probably you know many things about the distribution you are trying to sample from, but you want to be sure that the samples are really within epsilon, with epsilon say 10⁻² of the target distribution. Okay. From a nice picture of Langevin here, just to know how he looks like, and all the stuff that I will present here will be related to the Langevin diffusion. And I will start with very basic introduction. And if you have any question, please go on. I will try to be not very fast. So I mean, here the audience is such that I think that some part of my slides are useless, but still I want to present them in order to present my notation in order to be consistent with the remaining part of my talk. So the general goal is the following. We have a distribution pi, which is usually given by its probability density function, divided on the p-dimensional Euclidean space, and we want to sample a random vector, which is distributed according to pi. Okay, and what I would like to stress here is that the optimization, which is a topic of this workshop, can be seen as a particular case of sampling. And also what I would like to explain in the next couple of slides is that the sampling in high dimension is not easy. Even if dimension is like 10 or 20, it's not an easy task. Okay, so why do I say that the optimization is a particular case of sampling? Because if you imagine that the problem is to sample from a probability density pi, which is indexed by some parameter tau, so which is here, so this is, so it's the first time that I am giving a talk with my iPad, and I think that I have these nice things that I can write on the slides. Yeah, so here we have this parameter tau, which is a temperature parameter, and V is the potential function here. And basically, if we take this temperature parameter to go to 0, then we see very well that this probability distribution function will become more and more peaked around the minima of the potential function V. And this posterior distribution function will concentrate very close to the minimum points of the function V. So that's why for very small values of tau, if we manage to sample from this probability density function, we basically solve the problem of optimization. And this is a very important thing. So it has been already mentioned in a talk this morning by Francesca and by Tim, that very often if you want to solve a non-convex optimization problem, basically what you are doing is you are perturbating a little bit the optimization problem, and you are trying to sample from this tempered posterior distribution function. And there is a very nice paper by Ma et al. In 2019, which shows that in some cases, under some conditions on the potential V, sampling can be even faster than the optimization. Basically, if you have functions which are strongly log concave outside of a ball, of a compact ball, and which are smooth within the compact ball, you can sample more easily than optimize the function. Now, let me explain why sampling in a high-dimensional space might be a difficult problem. The easiest, I mean, when we talk about this with a student, with a master student, usually they say, yeah, but sampling is a simple problem. We have already seen in our master courses that we can use kind of inverse cumulative distribution function sampling, or we can use rejection sampling in a 2-3 dimensional cases. They work very well. But what happens if you use rejection sampling in a high dimensional situation? Basically, I just recall here what the rejection sampling is. So you want to sample from the target distribution pi, and what you know is a distribution nu, which is a distribution you can sample easily from. Okay? So basically, nu can be the uniform distribution on a hypercube. So the only condition that you need is that your target distribution pi, your target density pi, is upper bounded by a constant m multiplied by this sampling distribution nu. And then you proceed as follows. At each step, you sample a random vector from nu and a uniform random variable from 0, m. And then you compare u, which is between 0 and m, with the ratio of pi divided by nu evaluated at y. So y is this random sample from nu. So if you see that this u is smaller, then you accept and you set your x to be equal to y. Otherwise, you go to the previous step. Okay. So what one can show is that if capital K denotes the number of iterations needed for rejection sampling to stop, then this K is distributed according to geometric distribution with some parameter small p. So here p is not the dimension, it's just the probability here of acceptance. And one can see that the probability of acceptance here is 1 over m. Okay. So m, recall, is this constant which appears in the ratio of the target density and the sampling density. Okay. And of course, so since we have this geometric distribution, it also means that the average number of iterations needed for sampling, for rejection sampling to stop will be equal to 1 over this probability, which is equal to capital M. Okay. Now, what is this capital M in a high dimensional situation? Imagine that you are in a p-dimensional hypercube, and what you want to sample from is a uniform distribution on a set, which is included in this hypercube. Usually, what you manage to get relatively easily, if your set is nice, you manage to find a small ball included in the set. If you have a small ball included in this set, then you can compute this capital M, and it turns out that this capital M is usually 1 over the volume of a ball of radius r in a p-dimensional space. And basically, this quantity scales exponentially in dimension. Okay, so which means that in the rejection sampling, the average number of iterations that you will do in order to have acceptance will be exponential in dimension. And this is exactly what I mean when I'm saying that sampling in high dimension is not easy. It means that if you use traditional methods, then they will take exponential time in dimension. Fortunately, it turns out that if you use some more sophisticated, or I mean, they are not too sophisticated compared to some methods that we have seen here, but at least if we use some well-known methods, we can kind of avoid this exponential dependence on the dimension if the target density has some nice properties. In particular, when the target density is smooth and strong convex, we manage to avoid this exponential dependence. And this is exactly what I will try to explain now. Any question? No. So in the rest of this presentation, what I will do, I will focus on strongly convex potentials V only. I will review some results on kinetic Langevin Monte Carlo, and I will show also that the kinetic Langevin Monte Carlo is more general than the vanilla Langevin Monte Carlo, and I will show how the results for KLMC imply the results for LMC. And I will also mention some recent improvements that we have obtained for that. And the main philosophy in the results that I will present here is that we really wish to have upper bounds, which are very easy to understand, very easy to write. The dependence on everything is given explicitly. So when I say everything is essentially the dimension and the condition number here. And also we want all the constants to be small because, as I said in the beginning, what we would like to know is the number of iterations we have to do in our Langevin Monte Carlo in order to guarantee that the error is bounded by epsilon. Okay. So if we want a mathematical formula which provides us a number of iterations which is reasonably, say, small, I mean, it's always high, but not very high, then it's important to have small constants in all our mathematical results. Okay, so now what's the kinetic Langevin diffusion is? So let me first start by the probabilistic part of the story. Everything is continuous time now, and then I will go to the discretization of this process. So let W be a p-dimensional Brownian motion. And we consider this stochastic differential equation, which is a second order stochastic differential equation. Okay, so here all the derivatives that you see are with respect to t, so with respect to time. And L is the solution of the differential equation that we have here. Okay. Of course, it's a second order differential equation. The initial conditions should be the value of L and its derivative at the point 0. So we will denote by V the derivative of L with respect to time. So V kind of will be the velocity of this random field. And we will assume that L0 and V0 are given. They can be random, but they are independent on the Brownian motion W. So probably I missed some slide here, or yeah, I'm sorry. I think that I skipped this slide before. So yeah, what I wanted to mention also in the introduction that when I say that we will focus on strongly log concave distributions only, I define it explicitly what it means. So we will assume that our target density pi can be written as the exponential of a function minus f. Here, f will be defined everywhere on RP. So these distributions are obviously supported by the whole Euclidean space. And we will assume that this potential function f is 2 times continuously differentiable with the Hessian matrix, which is upper bounded by capital M times identity matrix and lower bounded by small m times identity matrix. Basically, it means that all the eigenvalues of the Hessian are between small m and capital M. Okay. Another way of stating this result is just to say that the gradient of f is capital M Lipschitz, and also that f is small m strongly convex. And so the goal that we have is to design a process which allows us to sample from some density mu, such that the Wasserstein 2 distance between mu and the target density pi is upper bounded by epsilon times this quantity. I won't go very deep into the explanation here, but just you can consider this factor square root of p multiplied by m here as some normalization, which makes all the results invariant with respect to the dimension and also invariant with respect to change of variable. Okay, because if you want to sample, say, from pi, you can also sample from rescaled versions of the pi, and you want to have a sampling guarantee which is scaling invariant. And so if you, for instance, if you use as mu the direct measure at the minimum point of the target density, then it can be shown that this inequality is satisfied with epsilon equal to 1. Okay, so another way of understanding this inequality is just to say I can solve the optimization problem, so I can guarantee this error here, and now I want to have a more sophisticated method which helps me to decrease the error by the factor epsilon. And a K quantity which we'll be focusing on is this condition number, which is small m over capital M over small m. So in practice, it can be very large. Why this quantity is important? Because, you know, I say this is the simplest situation where the function f is m strongly convex. Now, if you want to consider the setting where the function f is strongly convex, is log convex, but not strongly. So small m is equal to 0. One simple way to deal with this problem is to add a very small quadratic penalty to f. It will make it strongly concave, or strongly log concave, and then you can apply all this machinery in that case. But then you have to choose the amount of this quadratic penalty. And it turns out that this quadratic penalty should be very small. And the smallness of this quadratic penalty makes that this parameter kappa becomes very large. So that's why you need to have some upper bounds which kind of scale optimally with respect to kappa. The same situation appears if you want to sample from a distribution which is supported on a compact set. If you want it to be supported on a compact set, you can still add very small quadratic term to make it like Gaussian slightly far away from this compact set. And once again, this small m becomes very small and kappa becomes very large. So you need to show some results which are really sharp in their dependence on kappa. So this kappa is almost as important as the dimension is. Okay, so now I come back to this kinetic Langevin diffusion. So as I already told you, it's a second order differential, stochastic differential equation, which is written here. And of course, we can so make a small transformation denoting by Vt the time derivative of Lt. This new process LTVT becomes a diffusion process. In this case, it's a Markov diffusion, and it can be shown that under the condition of strong convexity and Lipschitz gradient of the function f, this diffusion process LTVT has a unique stationary distribution, which is given by this one. Okay, and here it's very nice because it's a product density here, and the first density is exactly the target that we are looking for. And the second one is Gaussian. Okay, some further properties of this kinetic Langevin diffusion. The solution of this differential stochastic differential equation exists if the function f, if the gradient of the function f is Lipschitz. It's one can prove that it's unique in the strong sense. And there are different terms for different terms are used for referring to this L. The main are the second order Langevin diffusion, kinetic Langevin diffusion, or underdamped Langevin diffusion. So I will mainly follow terminology which has been used in the paper by Zimmer, Eberle, and Guillen, who call this process kinetic Langevin diffusion. So it's the term that I will be mainly using in this talk. And also what I wanted to mention here is that this parameter gamma is the damping parameter. So when it goes to infinity, this first term disappears, and we find the first order stochastic differential equation, which is very well known as Langevin diffusion. So it's a vanilla Langevin or overdamped Langevin diffusion. Another important remark is that if the gradient f is constant here, then this second order stochastic differential equation has an explicit solution. It's a Gaussian process, and for every point t, we can very easily sample from this Gaussian process. Yeah, and finally, there is also this parameter t, and when we let gamma go to infinity and t go to 0, then we see that the first and the last term disappear in the equation, and we are left with a very well-known gradient flow. So it shows clearly that if we manage to have some results for this general Langevin diffusion process and its discretized versions, then by letting tau go to 0 and gamma go to infinity, we will recover results which are already known in the optimization and results which are already known for overdamped Langevin Monte Carlo. Okay, but I mean, it's really very curious because if you look in the literature, the results that have been obtained before, very often if you either make gamma go to infinity or let tau go to 0, the upper bounds explode. So you don't really recover the previous results. So this is, I think, an interesting branch of research, try to obtain results which are really strict generalizations of the results which exist in the optimization, for instance. Meaning that if you take tau equal to 0 in your result for MCMC, you really recover the result which is already available in the optimization literature. Okay, so I can skip this. Now, so as I promised, I will present all these sharp results for these different kinds of Langevin Monte Carlo methods. So first of all, this Langevin kinetic Langevin diffusion process. So I already told you that it has a unique stationary distribution, and this stationary distribution is a product one, with the first part being the target density, the second part being Gaussian distribution. Under this strong convexity condition on F, one can show that this kinetic Langevin diffusion process is also geometrically ergodic under some conditions on gamma. Okay, so this gamma shouldn't be very small because, as I think most of you know, if you take gamma very small, you get very close to the Hamiltonian Monte Carlo, and we know that the Hamiltonian Monte Carlo is not geometrically ergodic, right? So gamma shouldn't be very close to 0, but it turns out that if gamma is just larger than this term, then we have a quantitative upper bound on the mixing of the kinetic Langevin diffusion process. And this quantitative upper bound tells us that if we run two kinetic Langevin processes starting from two different initial distributions. So the first one starts from the distribution mu, the second one starts from the distribution mu prime. Then if we run these two processes up to time t, the distance between these two distributions will be very close to 0. It decays exponentially fast. And the factor that we recover here in the exponential can be written explicitly in terms of this constant, strong convexity constant mu and the parameter gamma, which is in the kinetic Langevin diffusion. Okay, so you see here that this parameter beta that appears in the exponential has somehow complicated form, but when gamma goes to infinity, so I said that when gamma goes to infinity, we recover the vanilla Langevin diffusion process. This gamma, this beta, sorry, converges to small m, to the strong convexity constant. It's known that for the Langevin Monte Carlo, for Langevin vanilla, sorry, so for vanilla Langevin diffusion process, it's known that the best possible exponent that we can find here is small m. Okay, so this is somehow optimal here. Now let's see what happens if we discretize this kinetic Langevin process. So of course, when we discretize a diffusion process, there are two key properties which will imply the quality of the resulting MCMC. These two key properties are, first of all, the mixing rate. So the original continuous time diffusion process should mix fast. And the second point, second important feature, is the smoothness of the path. Okay, because basically the fact that the diffusion process or continuous time process mixes fast means that you can choose a time window which is relatively small, and to discretize this very small portion of the continuous time trajectory of your process. And if the trajectory is smooth, it means that you can also choose a very large window or very large step size for your discretization. Okay, so these two properties are very important. As you have seen on the previous slide, the mixing properties are already explicitly analyzed. And concerning the smoothness of the trajectories of the paths of the process LT, that LT is given by this formula, where V is so the talk without my so you just switch off and switch on, or
yeah, the battery is okay.
The battery is okay.
Yeah, the battery was okay. Yeah, sorry for this.
Yeah, no problem. So yeah, so what I was just saying here is that this process VT, so if we look on the previous slide here, yeah, okay, it's here. So this process VT, you can see that it has just a drift term and a diffusion term. So the smoothness of VT is the same as the smoothness of the path of the Brownian motion. So it's kind of 1/2, up to 1/2, which means that the smoothness of the paths of L are 3/2. So combining these two properties of the kinetic Langevin diffusion process, it has been proved in this very nice paper by Cheng et al. In 2018 that if one suitably discretizes this kinetic Langevin diffusion process, one can get a sampling method which achieves an error epsilon in Wasserstein 2 distance after k iterations, and k here needn't be chosen very large. It can be just a term which is proportional to this condition number squared multiplied by epsilon, and this O tilde means that there are some logarithmic terms also involved. The logarithmic terms are always log of 1/epsilon. Okay? There is no dimension in the logarithm. So this is already very nice, but one can wonder whether this kappa square is optimal here. And also one can wonder whether we can have some non-asymptotic guarantees with small constants, as I discussed a little bit before. Also, yeah, I will present now how the discretization proposed in this paper by Cheng et al. Works. So the main idea behind is that I have already told you that in this kinetic Langevin diffusion, if the gradient of f is constant, then we can explicitly compute the solution of the differential equation. So what they propose in the paper, they say since for constant gradient f we can compute the solution, we will proceed as follows. So in the beginning, we fix some initial values, theta 0, v0 as we want. Of course, for v0, the best thing to do is to sample it from the invariant distribution because it's known here. It's just a standard Gaussian distribution. And then at each step k, we have already computed theta k and vk. So we just replace the gradient of f by the gradient of f at theta k. So it becomes the constant. And on the interval 0h, we can solve this differential equation explicitly. Okay? So we take just a small h, it's our step size of the discretization, and we define theta k plus 1 as L at the point h, for L being the solution of this stochastic differential equation. Okay, so the only difference with respect to the previous one is that the value of gradient of f here is theta k instead of being L of t. It turns out that it's very simple algorithm. For this algorithm, I have obtained a very sharp result that have been later on a little bit improved in this paper by Lionel Rieu-Durand and myself, where we have shown that if this parameter gamma, which is this friction parameter, is chosen sufficiently large, such that gamma times h is smaller than roughly 1 over this condition number, then we have this upper bound on the error in which the first term goes to 0 exponentially fast. This second term is small when h goes to 0. So basically, the second term is always used for fixing the step size h, so that this term is smaller than, say, epsilon over 2. And then the first term is made smaller than epsilon over 2 by taking k sufficiently large. Okay, so already this result improves a little bit upon the result in Cheng et al. Because the dependence on kappa here is better. And another improvement with respect to Cheng et al. Is that if you try to kind of find the optimal value of h and k from this theorem, you see that the optimal value of k depends only logarithmically on the initial distance between so the sampling distribution and pi, while in the result in Cheng et al. 2018, the dependence was polynomial here. So now, sorry. Yeah, now let me go to the randomized midpoint KLMC. So just in order to explain you historically in the past years, how does the evolution of these methods has been done. So in first papers, it was only the unadjusted Langevin diffusion or LMC that has been analyzed and shown that the dependence on dimension is really very attractive as compared to all the other methods which have been analyzed, MCMC methods which have been analyzed in the past. Then these papers that worked with KLMC shown that they can really improve on LMC. So it was really, for me, it was really a first step of improvement, which was very important. And next step has been achieved by introducing this randomized midpoint method. And so, you know, when you go from LMC to KLMC, you really change so you change the continuous time process. But then for a given continuous time process, you can always wonder whether your discretization scheme is good or not. As mentioned this morning, for instance, one can use Mersheim discretization instead of the Euler one. If the gradient of f has some additional smoothness than some other discretization schemes exist. So the discretization is always one of the, say, tools which with which you can play in order to improve sampling. Yeah. Yeah.
Probably you just answered it, but so basically the first row can be seen as exponential integrator or something.
Yeah. So now, yeah. So what I was mentioning is that in this literature on non-asymptotic guarantees for this discretized Langevin processes. This paper by Shen and Li was really a breakthrough because they showed that they really can improve upon the previous methods. And their idea was simply to introduce a randomized midpoint, which basically means the following. You use the previous algorithm. This is, here you have exactly the same differential equation as before, but instead of going up to the point h, you go up to the point u times h, where u here is a uniform, is a random variable drawn from a uniform distribution on 0, 1. Okay? And then once you have this intermediate point, you still once again solve the same differential equation, but you replace theta k by this intermediate point. And it turns out that if you use this, the result is much better. And this better result is written here. So while for the non-randomized midpoint method for KLMC, the optimal bound of this type were of this type, for the randomized midpoint method, you obtain something which is much better. So dependence on epsilon, here you see it's improved. So it works, it's epsilon to power 2/3 instead of 1 over epsilon. And the dependence on kappa is better as well, okay, because you have a much smaller power of kappa here as compared to the power of kappa, which is here. Now, let me just see very quickly, just from a technical point of view, why this randomized midpoint method is better than the previous one. So why does it work actually? Because the idea is that if you look at the KLMC, so when you pass from the step k plus 1, from step k to k plus 1, your theta k plus 1 is written as this form. So here you have something which is computed on the previous step plus this Gaussian term. While what you would like to do ideally is to solve a continuous time differential equation, in which case you would compute this L bar, which has exactly the same form, the same difference. The only difference is that this term in which we have the gradient is this continuous integral, okay, over 0h. So when you compute the difference between these two in order to evaluate the error of this sampling algorithm, you can see that there will be a first term of error, which is very good. It only depends on what happens at 0. And there is a second term of error, which depends on what happens between 0 and h. Both of them are random. And it turns out that when you analyze the error, the largest term comes from the fact that these two errors are correlated. And the randomized midpoint method, what it tries to do is just to replace this term by some term, which has much smaller correlation with the first term. Okay, so so quickly, the result that I have shown here, which has been obtained in this paper by Shen and Li, so it was really a breakthrough because it proved that with this randomized midpoint method, we can have qualitatively and quantitatively better bounds on the number of iterations. However, the upper bound, which is given for the error of the sampling here, it was implicit, sorry. Because if you read the statement of the theorem that I wrote here, so basically they say that there are some constants, there are some powers of h for which this kind of error can be shown. Now, no constant is explicit in their results, and also the choice of h in their results is not explicit. So if you want to use this method, even in small dimension in practice for choosing the step size, you cannot really find some guidance in their theorem. So the improved versions that we have is here. So there are all constants here properly written. They are all very small, and the result is very nice. Yeah, another difference is that in their result, they assume that the initial value of the Langevin MCMC, which is used here, is the minimizer of the target function. So the initial point theta 0 is just the minimizer of the potential function, and the V0 equals 0. This is not a real condition. So here we have also a clear evaluation on how the distance from the initial distribution from the target one enters into the error. Okay, so just to conclude, so these are the first results which are obtained in the case where the function is strongly log concave and Lipschitz continuous gradient. Of course, the main goal is to use these simple results in order to get extensions in more, say, broad situations where the target density is just log concave. It can be compactly supported. It can be kind of smooth within a ball and strongly log concave outside the ball. And also something that I am really interested in, but this part seems to be really the hardest of the list that is written here, is to get similar results in the case where the target density satisfies some functional inequalities like log Sobolev or Poincaré. Okay, thank you very much.